and then we can start.
Okay, you can go.
Okay, so I'm one moment that I'm perfect. So let's start with the first paper. So welcome all to this parallel track in the ICCSA conference. And we start with the first paper that will be presented by Sidonie Costa from ICCSA, Portugal. And the title is The Effect of Phase Change During the Deposition Stage in Fused Filament Fabrication. So you can start, Sidonie. Thank you.
Okay. Can you see the presentation?
Yeah.
I try to share.
Yes, you can.
Yes.
Okay.
Okay. Thank you.
You're
so my name is Sidonie, and this work is about the effect of a phase change during the deposition stage in fused filament fabrication. This is the outline of my presentation, so I will start with the motivation. Fused deposition modeling or fused filament fabrication is a rapid prototyping process where parts are constructed layer by layer without any mold from a computer model. In the physical process of fabrication, a polymer filament is fed through a nozzle and deposited onto the support. The head then moves around in the XY plane and deposits material according to the part geometry. The movements of the head are controlled by the computer in accordance with the 3D model slices. The platform holding the part then moves vertically in the Z-plane to deposit a new layer on top of the previous one. These are the typical objectives in this type of technique, but this work is more related with the dimensional accuracy controlled by the filament deformation and the mechanical performance controlled by the quality of bonding. On the other hand, in order to avoid excessive deformation, we need lower temperatures, but in order to improve the quality of bonding, we need higher temperatures. So we need to find a compromise between heat transfer, bonding, and creep deformation, and to establish an interrelation between them. Respecting to the modeling of the process, first, the heat transfer phenomena were analyzed by using the Abacus software. This study allowed concluding about the main conditions that control the temperature evolution. So based on these conclusions, a heat transfer analytical study was made. Then the energy balance was defined, translated into a differential equation, and solved. We obtained an expression for temperature that can be used for any filament. Respecting to the adhesion, the model of Yang and Picciumani is used to compute the bonding degree between all pairs of adjacent filaments. In this model, we have an expression that depends on temperature and allowed concluding if the bonding was achieved or not. The creep deformation was also studied with Abacus software and allowed concluding that the deformation is very low. So this was neglected. Then an interrelation between heat transfer and bonding was established. So the degree of adhesion is computed. While it is lower than 1, the thermal contact conductance is low. When the bonding is achieved, the thermal contact conductance is increased to favor the heat transfer between the filaments. Finally, since the filaments are progressively deposited, the initial and boundary conditions must be updated along the process. So an algorithm is required to make this procedure automatic depending on the geometry, the build orientation, and the deposition sequence. All these components allowed obtaining a computation code for the modeling of fused filament fabrication. So with this model, it is possible to obtain the temperature evolution and the regions of good and poor adhesion for any part geometry. And the predictions of the model were generally in good agreement with the experimental data. So with the computer model, we can obtain temperature results, for example, a graphic with the temperature evolution of all filaments of a given sequence, or we can obtain an animation with the temperature values in the whole part as deposition proceeds. For example, we can see the fast cooling down due to the small dimensions of the filaments, and we can see the heating of the colder filaments by the new hotter deposited filaments. It is also possible to obtain bonding results, for example, with this ABS part and this filaments orientation. We have 6 possible build orientations. So with the typical extrusion temperature of 270 degrees, all parts will have a good quality. But if the extrusion temperature decreases to 260 degrees, problems of adhesion appear for orientations A and B due to the variations in filament length. If the extrusion temperature is decreased again by 5 degrees, problems of adhesion also occur for the over orientations. Despite the practical usefulness of this model, this method can only be used for amorphous materials such as ABS. So in the case of partially crystalline polymers such as PLA, a phase transition from the melt to the solid state must be considered. And during this phase, the temperature remains constant. So the objective of this work is to include a phase change material in the calculation of temperatures. Then the phase change condition was defined, translated into a mathematical equation, and we obtained an expression for the instant at which the phase change ends. I will present 2 case studies. So the first example concerns the deposition of a single PLA filament. This is the temperature evolution at a cross-section with and without phase change. So the phase change lasts 0.75 seconds, which results in a maximum temperature difference of 13.9 degrees. The second example deals with the deposition of 10 filaments. So this figure shows the temperature evolution of filament 2. We can see the peaks of temperature due to the deposition of new hotter filaments. So we have the 2 same cases with and without phase change. And we have a higher maximum temperature difference of 18.9 degrees due to the contacts between the filaments. If the same sequence is considered, but with ABS and PLA materials, the maximum temperature difference is even higher due to the differences in material properties. We are talking about 39.1 degrees. And the ABS filament cools faster, which means that this PLA is a better option to favor the adhesion between the filaments. So as a conclusion, in a previous work, a MATLAB code was proposed to simulate the heat transfer and the adhesion in fused filament fabrication. In this work, a phase change was studied and included in the computer model. The results show that the phase change influences the temperature evolution, and consequently, the selected material is an important process variable. The next step is to define a healing criterion for PLA with the aim of studying parts made by ABS and PLA materials, the 2 most used materials in fused filament fabrication. Thank you.
Okay, so thank you very much for your interesting presentation. Let's see if there are some questions from the audience. It seems not. Let's have a look at YouTube to see if there are people.
There is nothing, Davide.
Nothing? Okay. So I can ask a question. So the final goal of this research could lead to some guidance for people that may be not so expert in fabrication in using 3D printers.
Sorry, I don't understand the first part.
With this simulation of the temperature for adherence, is it possible to come with some guidance for people that is not very expert in printing objects through 3D printers, suggesting, for instance, in which direction it's better to print, how to orient the model for obtaining a better result, and so on.
Yeah, yes, the objective of this model is to guide, to have a guidance for the users in selecting the best process variables. Another task of this work is to use optimization in order to find the best process variables. For example, deposition velocity to minimize the manufacturing time, or to maximize the adhesion, to minimize the processing temperatures in order to minimize manufacturing time. So yes, the main objective is this. But before this, it is important to include like this phase change, the possibility of other materials. So there is some work before before
Still
this.
some other variables to consider.
Yes.
Okay, so thank you very much for your
Okay.
presentation. And okay, I think that we can go ahead, but I'm just having a look, but it seems that the presenter of the second paper is not here. It's easy to understand who is, because it's the only author of the paper. So, Michael, is it okay with you to start now and to wait maybe?
Okay.
Okay.
Now I'm trying to share. Can you see my presentation now?
Yeah. Yes.
Oh, okay. So can I start?
Yeah. Please.
Hello there, colleagues. My name is Mikhail. I'm a researcher for St. Petersburg Institute for Informatics of the Russian Academy of Science. My presentation is devoted to the correct selection of artificial parameters of the numerical schemes, especially for the parabolic equation method. It is well known that any numerical method has a set of artificial parameters, such as geometry of the computational grid, size of the grid cells, approximation order, convergence threshold, and so on. Those parameters directly affect the accuracy and speed of calculation, and the problem of choosing the computational parameters depending on input data is not properly addressed, especially in complex software systems. In this paper, we consider high-order numerical method of the parabolic wave equation. It is widely used in various areas of wave propagation studies, such as tropospheric radio wave propagation, underwater acoustics, scattering, optics, quantum mechanics, geophysics, and so on. Schematic description of the problem for tropospheric propagation and underwater acoustic are depicted in figures. Mathematical statement of the problem is as follows. We start with two-dimensional Helmholtz equation defined on finite or infinite domain. We are seeking the solution on a finite domain, but the bounds of this domain may be transparent. We use split-step PADE method for the approximation of the propagation operator. PADE approximation order may be chosen arbitrarily within this method. Transversal operator is discretized by the fourth order scheme. Thus, we have the following artificial parameters in the considered scheme: grid step, delta x and delta z, and PADE approximation order. Next, we provide the dispersion analysis for the considered numerical scheme. We substitute the discrete plane wave to the considered numerical scheme. We express discrete horizontal wave number as a function of computational parameters and propagation angle. While horizontal wave number for the original Helmholtz equation is follows. Comparing the original and discrete dispersion relations gives us an opportunity to estimate the phase error of the numerical scheme at each propagation step. This figure represents the dependence of the horizontal wave number on the propagation angle for various approximations. Dotted line means the original Helmholtz equation. One can easily see that the increased accuracy of the approximations leads to increased maximum propagation angle that can be handled by the approximation. The same picture with relative errors. Now we are ready for the formulation of the parameter selection algorithm. It consists of the two steps. First, we need to estimate the maximum propagation angle based on the geometry of the problem. Then we minimize function g, which represents the time complexity of the algorithm. Now we analyze the result of the proposed algorithm for various values of the maximum propagation angle and approximation orders. In this table, we see result for angle with 3 degrees, 10 degrees, 20 degrees, and 45 degrees. One can see that first, that increasing the approximation order of the finite difference numerical scheme has a significant impact on the performance. PADE 7-8 approximation yields 3 orders faster numerical scheme than standard Crank-Nicolson approximation. Increasing the approximation order increases the maximum propagation angle and reduces computational time. Standard Crank-Nicolson numerical method can only be used for very small propagation angles. And some conclusions. Discrete dispersion analysis can be efficiently applied to automatic computational parameter selections. The method is useful for the numerical solution of a class of propagation problems. The method is based on the theoretical analysis of the numerical scheme and uses a priori information such as maximum propagation angle about the propagation medium. Numerical scheme allows an arbitrary approximation order for both coordinates. The numerical propagation method under considered and presented under consideration and presented parameter selection are implemented as Python 3 open source software library, which is available by the link. Thank you for your attention.
Okay, thank you very much. Again, I don't see questions from the audience, and maybe also from YouTube we don't have any. And so I would like to ask a question. You show that your method has increased the efficiency in the computational time. Can you give us some examples of how much time it takes to conclude a normal size computation for this method and from the previous one, so the ones that you compared against?
Okay. No, this method is no, the numerical scheme under considerations, not exactly mine. Mine is the method for determining the optimal computational parameters. But we can see, for example, we can compare the standard Crank-Nicholson approximation, which is widely used, and the higher order Padé approximations, which was considered in this paper. I introduced the function g, which is defined very simply, and it directly depends linearly on the time of computation. It is big O for the time complexity. And one can see that higher order parabolic approximations yield 3 orders faster algorithms, 3 orders faster results than standard Crank-Nicholson scheme.
Okay, so thank you. And I don't know if there are no further questions. I think that we can move on. Thank you very much, Michael. So I would ask, in the meantime, it doesn't seem to me that the second presenter has appeared. No, indeed. So we move on and we introduce Igor Morais, that is going to present a paper that is entitled "A Biased Random K Genetic Algorithm for Bandwidth Reduction." So please, Igor, you can share your screen and you can present your paper. Thank you.
Okay, can you hear me?
Yes.
Yeah. So, put my presentation. Oh, sorry. I'm Igor Morais from the Federal Center for Technological Education of Rio de Janeiro, and I'm random key genetic algorithm for the bandwidth reduction. We made this paper with Professors Pedro, Diego, and Sanderson. And at first, I'm going to introduce the problem. The problem has applications for solving linear equation systems, a method to apply to sparse, squared, and symmetric matrices. Some methods can reduce the quantity of iterations made into convergence, as used to solve partial differential equation systems, which can be approximated by linear equation systems. The bandwidth of a matrix is the maximum distance between elements to its diagonal.
We lost Igor.
In an adjacent matrix.
Igor, can you repeat the last sentences, because we lost you at one point? Can you go back? Yeah. Thank you.
The bandwidth of a matrix is the distance between its elements to its diagonal, horizontally or vertically measured. For our method, we used a graph representation which consists in an adjacency matrix. For every non-zero value, the cost of a solution is given by the maximum absolute difference between these adjacent labels, and the object absolute difference. As an example given below, the matrix label and the distance from the row, which has the label 1, is 1 for the diagonal, and the labels in the graph for solving the biased random key genetic algorithm, which is a meta-heuristics approach consists of combining heuristic procedures with a method to avoid local optima. And the genetic algorithm is the base for the BRKGA. And given a population of solutions which are called chromosomes, the genetic algorithm uses the procedure for combining solution, which is called crossover. This population is divided into groups, one, the elite set and a non-elite set, based on the value of the cost function. The random key genetic algorithm consists in encoding every gene in a chromosome to a value between 0 and 1, like the example given below. The biased one is an addition that increases the probability of an elite parent passing its genes to a new solution in the crossover. For the initial population, we use the constructive approach, which uses a random breadth search, choosing at random one vertex with the label 0 to start, and successively choose another labels for the adjacent vertex. Here we start with an empty graph and choose at a random position for the 0 label. Then it has two possibilities, and we choose one for the at random and put the label 1. Then the label 2. Then the only possibility is to put the label 3, and then we put the label 4. It's the last one. This procedure is repeated until the size of population is reached. The decoding process in the biased random key genetic algorithm is necessary for converting the solution into a real solution of the problem, converting the encoded solution into a real solution. For this one, we sorted the encoded solution based on its random case, and we calculate the cost function for the problem. For improving convergence of the method, we use the local search procedure. We need two sets of for swap and the labels of vertex. As proposed by Lim, we use the concept of critical node, which is the ones with the maximum difference in the labels, and the minimal nodes, which are the ones with the minimal difference. In this example, we choose to swap the 4 and 3, because 4 and 1 are the critical nodes, and 3 it's a minimal node. And if the solution is if the cost function is reduced, the solution is accepted, otherwise it's discarded. For the computation experiments, we use the Core i7 with 4.2 gigahertz and 32 gigs of RAM. And for the language, we use the C++ and the framework for the BRKGA from Tozo and Resende. The parameters for the BRKGA is the size of the chromosome is n, and this n is the number of rows of the matrix has. And the population size is 1,000, and the probability of an elite passing its genes is 0.5. And for every 100 generations, the elite set is swapped in 2 population sets. For comparison, we used 4 methods: the reverse cut-Hill-Markey, the RCM, the reverse breadth search, the GRASP, and the dual representation simulated annealing. In this first set of matrices, we only lost to the last 2 and to the HOR 131 here, to GRASP and RCM and RBFS. To the RSA, we were surpassed in all solutions. And for the second set of matrices, we lost only on 2 and surpassed all the others from GRASP RCM, but lost again to the RSA. The BRKGA outperformed the GRASP and the reverse cut-Hill-Markey, but was dominated by the BRKGA. As a future work, we want to develop a parallel version of BRKGA to improve time for convergence in a good solution. Thank you.
Okay, thank you very much, Igor. Again, let me have a look to see if there is any question. It doesn't seem so. Okay, so I would like to ask you if you can elaborate more on this parallel version of the algorithm. Currently, do you think that where do you think that the algorithm can be expressed in parallel?
We can make parallel versions of the constructive, which construct a population of 1,000. We can make one population by thread or by computers in this version, and we can parallelize the local search procedure and the decoding procedure for some solutions until the population, until one generation is finished.
So, okay, running different instances like in a farm approach, different instances of the same algorithm, but internally it would be kept sequential, right?
No, we can construct for a chromosome, we can construct every chromosome in the initial phase in a processor, in a thread.
Yeah, okay. Yeah, and then continue the, yes, okay.
And then continue as a sequential.
Okay. And the second presenter is not here, so I think that if there are no further questions, this concludes this session, and then we are going to meet again here at 5:30. So we have a 25 minutes coffee break. Unfortunately, everyone will have his own coffee. Okay,
We are still on YouTube until the last session. Okay.
Okay.
Everyone.
So we are going to deactivate our webcams. Thank you very much. Bye bye.
Bye bye. Bye.
Ok, è andata. Va bene, allora io stacco un secondo e poi ci rivediamo qua, se no insomma 25 minuti
Hi, this is working. Hi.
Hi Davide.
Hi Sara.
Non ti sente?
Mi sentite adesso?
Ok, vai.
Okay. No, niente, abbiamo qualcuno di... Sì, aspetta.
Yeah, I think that they are all here.
Okay, so it's perfect. May I ask you to change your display name? In this way, we are able to identify you and also to understand who is the presenter about among the many authors that all the papers have. Magari. Okay.
You can open your videos and microphones if you want now.
Forse qualcuno è lontano dal computer, cioè se è connesso ha mollato tutto così.
Può essere, intanto iniziamo tra un po'.
No.
Però sembrano esserci tutti.
Terzo. Sì.
Hi.
Hi.
I'm José Luis. I'm talking about 550.
550. Yeah, you are the third one.
Yeah.
The third paper. I'm here. So the presenter of the first paper is here.
It's your son.
Yes. He's wandering around.
I don't see anyone from the first one.
Yeah.
But we still have 4 minutes, so
Yeah.
we can wait.
We wait a little bit. Otherwise, we start from the second one. That instead, I see that there is Lydia here, and then we hope that they are going to catch up.
Yep. Davide, non ti sento più.
Sì, l'ho staccata apposta.
Ah, ok, scusa. Hi. Ok.
Hello.
Forse non ci sente?
Ma guarda, io a occhio direi che Lidia.
Sorry? Hi.
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 Are you Lidia, Andre?
Yes.
Yes, okay. We are waiting for the presenter of the first paper, and yeah. So we wait a couple of minutes. Otherwise, you will be the first speaker.
Okay. You or someone of your colleagues?
It's me.
Okay.
Yeah. Also, Isabel is here, and she's one of your co-authors, right?
Yes.
Okay. Ha. We have two Marcela Velasquez.
Okay. Hi, Marcela.
Hi, Marcela.
It's freeze.
Yes.
Yeah.
Hi.
We lost Marcela.
Hi.
Hi.
Okay, we see two two of you because we have one square here with your photo or a video freezed, and the other one that takes your audio connection. So maybe you have two tabs open on the same room, or two browsers. I don't know.
Marcela?
Hola, disculpen, lo que pasa es que yo hablo español y entonces yo voy a entrar conectada con un intérprete para poder hacer mi conferencia porque la persona que iba a ayudarnos con la interpretación de mi equipo de investigación le dio el COVID y entonces, sí, está grave. Entonces,
Really sorry.
voy a entrar con un intérprete para poder comunicarme con ustedes.
Who is the interpreter?
I speak Spanish. I can translate what she says.
She have an interpreter?
Yeah, because the member of the group that was going to talk in English is ill by COVID.
Yeah, I understand that part.
Okay.
I'm really sorry about that. But I think we can start, Davide.
Yes.
Okay.
So, okay, so the first paper will be the second one, actually. So the presenter will be Lidia Andre, if I pronounced it well. And the paper is a special modeling of black scabberfish fishery off the Portuguese coast. So you can start, Lidia. The stage is yours.
Can you hear me?
Yes, loud and clear.
Hello, my name is Lydia, and I'm going to present the joint work called Spatial Modeling of Black Scabard Fish, Fishery of the Portuguese Coastline. This is the outline. Usually, a way of getting information about geographical distributions of a species or their diversity is through research surveys, although for deep water species, such as the black scabbard fish, the surveys are scarce, and therefore the monitoring of the population relies mainly on fishery data. In particular, in Portugal, the spatial distribution and abundance of the BSF species is mostly unknown, and so the focus of this work is then modeling the spatial distribution of the BSF species relatively biomass along the Portuguese coast. The data in study corresponds to the BSF catches by fishing hole of the longline fishing fleet of the fish grounds of the zone of Lisbon, and we can see that on the picture on the right. It is also the data from the second semester from 2009 to 2013. The data also included the location of each fishing hole, the corresponding vessel identification, and the depth out of the locations where the fish was captured. The vessels were also grouped into 3 levels according to their tonnage. And in order to meet the Gaussian assumption that is required by the traditional statistical techniques, a box-cock transformation of the catches was used. First, a geostatistical analysis was then performed to find if the data were isotropic. Data being isotropic means that the dependence between sampling locations only relies on the corresponding distance and not on orientation. And therefore, a test where the null hypothesis was the presence of isotropy was performed, and a p-value of 0.96 was achieved. Then the hypothesis of isotropy was not rejected. After doing a preliminary analysis on the data, we proceeded to the modeling of this data. This was done under a Bayesian framework because of its flexibility. And in order to avoid the computational issues and costs of MCMC methods, the stochastic partial differential equation under the integrated nested Laplace approximation was considered instead. This methodology represents a continuous Gaussian field using a discretely indexed Gaussian Markov random field, considering SPDA whose solution is a Gaussian field with a Matern covariance that is defined here. As said before, the box transformation was used for the catches, and so the observations follow a Gaussian distribution with the response mean at I and negative variance sigma square E. Several linear models were considered. One of the models is presented here, and it includes the variable group tonnage as a random effect and is with a sum to 0 constraint. The variable depth as a fixed effect and some special component. The other 10 models considered are summarized in the table, and the variable, for instance, the variable group tonnage was considered either as categorical or a random effect, whereas the variable depth was always considered as a fixed effect when included in the model. Being this modeling under a Bayesian framework, prior distributions have to be chosen. And so for the intercept and the regression coefficients, a normal distribution with mean 0 and precision 0.001 was used, whilst for the precision of the Gaussian distribution, observation, a gamma with these parameters was used. For the precision of the variable group tonnage as a random effect, more informative priors were used. For models where a special component is not considered, truncated normal with mean 0 and precision 0.1 was used, and for models where a special component is included, a gamma taking into account the variability of the model with just a special component was used instead. These two priors are a bit more informative since we find that this variable is highly sensitive to the choice of the priors. Regarding the special hyperparameters, the penalized complexity priors were used. These priors try to penalize the deviation from a base model where the range is the infinity and the marginal variance is 0, and they are constructed as probabilities. In our analysis, we consider the probability of the range being lower than 30 to be equal to 0.1, and the probability of the marginal standard deviation greater than 10 to be equal to 0.01. The SPDE approach also relies on a finite element method to approximate the Gaussian field by the Gaussian Markov random field, and this lies on a triangulation of the spatial domain through a mesh. Additionally, the constraint of the mesh is an important point of the process, and some considerations have to be taken into account. The mesh considered in our analysis is the one presented here.